welcome to this presentation on a groundbreaking research paper titled Absolute Zero Reinforced Self-Play Reasoning with Zero Data. This paper was published and written by a talented team of researchers from institutions like Tsinghua University and Pennsylvania State University. It was published in 2025 and was made publicly available as of 9th May 2025. So what's this paper all about? Imagine building an AI to solve tough problems or tackling mathematical equations or even coding a game. Right now, to train that AI, you need a huge pile of examples. Think like thousands of math problems or code snippets, all created by humans. But here's the catch. As AI gets smarter, we need more and more of these examples, and humans just can't keep up. It's like trying to fill a bucket with water using an eyedropper. It's slow, tedious, and expensive. This is a major bottleneck in AI development today. This is where this paper steps in with a brilliant solution. They introduce something called the Absolute Zero Reasoner, or AZR for short. AZR is an AI model that doesn't need any human-made data to learn reasoning skills. Instead, it creates its own problems, solves them, and improves all by itself. Picture a student who does not need a teacher because they can create their own homework, graded too. The result, AZR can perform just as well or even better than models trained with tons of human data. This could change the game for AI, making it faster, cheaper, and more independent. Before we get into the nitty-gritty, let's cover some basics so we are all on the same page. First up is reinforcement learning, or RL. RL is basically how an AI learns by trying things out and getting feedback, kind of like training a puppy. If a puppy sits down when you say sit, you give it a treat. Over time, it figures out what works. In RL, the AI takes actions, earns reward for good results, and tweaks its strategy to maximize those rewards. Next, we have got large language models, or LLMs. These are the brains behind tools like ChatGPT. They are trained on massive amounts of text and can write, read, or even chat with you like a human. They are super powerful, but they usually need a lot of data to get going. So finally, let's talk about reasoning tasks. These are like challenges which require logical thinking, like solving a math problem that said 2x plus 3 equals 7, or writing a program to sort a list of numbers. They are tricky because they involve multiple steps and real problem. So how have researchers tackled these tasks before? They have used two big approaches, which is supervised fine-tuning. This is like giving the AI a stack of solved tests. It studies problems and their answers. Like, here is a math problem and here is how to solve it, and learns how to copy those solutions. Reinforcement learning with verifiable rewards, or RLVR. Here, the AI tries to solve problems on its own, gets a reward if it's correct, like a gold star for writing the right answer. But the problem still comes from humans. Both methods work, but they hit the same wall. They depend on human-made datasets. As AI gets more advanced, we need bigger datasets, and humans simply can't produce them fast enough. It's like asking one person to write a textbook for every new subject. It just does not scale. This paper just comes up and says enough of that, and AZR breaks free of human data. Instead of waiting for us to spoon feed it examples, AZR generates its own tasks and learns from them using reinforcement learning. It's a bold move for tackling the scalability problem head on, and I can't wait to tell you how it works. So let's get into the heart of the paper. The core idea behind AZR that it's built on something called as self-play. You might have heard self-play in games like chess, where an AI plays against itself to get better. Imagine a chess player practicing by controlling both sides of the board. Over time, they'd master every move. AZR does something similar, but for reasoning tasks. Here's how it works, step by step, with an analogy. Picture a student who is determined to ace math. Instead of relying on a teacher, the student makes up its own problems, like let's say 5 times 12, or solve x square minus 4 equals 0. Then they solve them and check their work. If they are right, they feel great and move on. If they are wrong, they figure out why and try again. Over time, they get really good at both problem making and solving them. This is basically AZR in a nutshell. AZR has two main parts, the proposer and the solver. The proposer is like a student inventing problems, and it creates tasks like write a program to calculate 5 factorial or solve this equation. The solver is the one answering those tasks, like it might write some Python code or say x equals 2 or negative. But how does this check its work? Enters the code executor, which is the third piece of the puzzle. Here it acts like an automated grader. For coding tasks, it runs the program solver, let's say 5 into 4 into 3 into 2 into 1, and checks if it spits out 120. For math, it plugs the answer back into the equation to see if it holds. If the solution is correct, the AZR gets a reward. If not, it learns back from the mistake. This sets up a feedback loop, and the proposer generates a task. The solver tries to crack it, and the code executor gives the thumbs up, or thumbs down. The feedback flow, uh, the feedback flows back. This sets up a feedback loop. The proposer generates a task, the solver tries to crack it, and the code executor gives the thumbs up or thumbs down. The feedback flows back, the proposer gets better at making useful tasks, the solver gets sharper at solving them, no humans needed. So, as we go ahead, so why does this matter? Because AZR can learn to reason, code, math, you name it, without a single human example. It's like an AI that builds its own ladder to climb higher and higher. The results speak for themselves. AZR matches or beats models on huge datasets, proving that it does not need a mountain of data to reach the top. That's the brilliance of Absolute Zero. It's a new way of thinking about AI training. The one that's self-sufficient, scalable, and ready to push boundaries. Alright, we have gotten the bigger picture. Let's dive into the AZR, how it actually works. At its core, AZR is a self-reasoning system that learns through a process called self-play. It's like a student who not only solves problems but also creates them, getting better at both over time. Let me break down the key roles that AZR plays: the proposer, the solver, and the code executor. These three roles work together in a loop where proposer creates a task, solver tries to solve it, and the code executor checks the answer. Based on the feedback, the proposer adjusts its task-making strategy, and the solver improves its problem-solving skills. It's a continuous cycle of self-improvement, all without human intervention. How does there's one more question which may arise, that how does AZR decide what tasks to propose and how to solve them? It all comes down to reinforcement learning, which we have touched on earlier. In RL, the AI learns by maximizing its rewards. Here's how it works in AZR. Reward for the solver, this one's straightforward. Like if the solver gets the answer right, it gets a reward of 1. If it's wrong, it gets 0. Reward for the proposer. Here it is trickier because the proposer's goal is to create tasks that are challenging but solvable. If the solver always gets a task right, the task is too easy and the proposer gets no reward. If the solver always gets it wrong, the task is too hard and again no reward. Sweet spot is when the solver succeeds about half the time. In that case, the proposer gets a reward based on how often the solver succeeds specifically, but only if the success rate is between 0 and 1. I know that sounds a little bit confusing, but yeah, that's exactly what the proposer is trying to do. It tries to create that perfect balance. Now, how does AZR generate these tasks? It uses something called as task types. There are 3 main types of tasks used: deduction, abduction, induction. AZR generates these tasks in categories, and the solver learns to handle each type. This diversity helps AZR become a well-rounded reasoner. There is a little bit talk we can have behind the math of this, where I'll try to keep it simple. Where at the heart of AZR is reinforcement learning, which means it's trying to maximize the total rewards over time. But the key equation here is the objective function, which tells AZR what it's trying to achieve. So here I will be attaching the PDF which contains all the mathematical formulas related to this paper in the description or in the comment section. The reward is easy: 1 if correct, 0 if no. For the proposer, it's more nuanced. The proposer reward is based on the solver's success rate. AZR starts with simple tasks like basic math or easy code and gradually makes them harder as it improves. It's trained over many iterations, each time refining its proposer and solver. The whole process is automated, with the code executor providing instant feedback. It's like a self-improving loop that keeps getting smarter. Alright, now let's talk about AZR and how it works, and let's talk about the results. Did this self-learning AI actually perform well? Spoiler alert, yes, and in some cases it even outperformed models that were trained with thousands of human-made examples. The researchers tested AZR on 2 main types of tasks: coding and math. For coding, they used standard benchmarks like HumanEval, which is a set of coding problems similar to what you'll find on platforms like LeetCode. For maths, they used problems from competitions like AIME and the AMC, which are pretty tough. Here's the cool part: AZR was compared to other models that were trained using traditional methods like SFT or reinforcement learning with human provided data. And guess what? AZR either matched them or beat them without using any human data at all. Let me show you some numbers. On the human eval coding benchmark, AZR achieved a score of 71.3, while models trained with human data score around 73.2 to 80.5. That's close, but remember, AZR did this without any help. On math tasks like AIME, AZR scored 13.3%, which might not sound high, but it's competitive with other models that had access to thousands of math problems for training. Even more impressive is that on some math benchmarks like AMC 23, AZR scored 52.5%, beating many models that are specifically trained for math. And on coding tasks like Live Code Bench, AZR scored 25.3, again rivaling models with human data. What does this mean? It shows that AZR self-play mechanisms works. It can generate its own tasks, solve them, and learn from the process, achieving results on par with traditional methods. This is a big deal because it means that we might not need massive human curated data sets to train powerful AI models in the future. So let's have a few minutes of discussion over this and analyze it and finish this off. So why does this all matter? Let's think about the implications. First, AZR's ability to learn without human data solves a huge problem in AI development, the data bottleneck. Right now, training AI models requires tons of table examples which are expensive and time consuming to create. But with AZR, the model generates its own data, learns from it, and improves over time. This could make AI development faster, cheaper, and more scalable. Second, AZR self-play mechanism allows it to explore and learn in ways that traditional methods can't. Because it's generating its own tasks, it can focus on area where it's weak and push its own boundaries. It's like a student who knows exactly what they need to study to get better. But like any research, there are limitations. For one, AZR is computationally intensive. It needs a lot of processing power to generate and solve tasks repeatedly. Also, while it performs well on coding and math, while we don't know yet how it would perform in certain other domains like natural language tasks or creative writing. The researchers mentioned that future work could explore applying this approach to different areas, which is really exciting to see. Another thing to consider is safety. Since AZR is generating its own tasks, there is a risk that it could create harmful or biased content. The paper briefly mentions this, and it's something that needs careful attention as this technology develops. And as we wrap this up, we'll talk about how much future work can be done in this and in the conclusion. Where AZR is seen as a groundbreaking step in AI research, it shows that AI can learn complex reasoning skills like coding and math without any human provided data by generating and solving its own tasks. This can revolutionize how we train AI models and making the process more efficient and scalable. The key contributions from this paper are the absolute zero paradigm, a new way or to learn through self-play without external data. The AZR system, where a model that proposes tasks, solves them, and learns from verifiable feedback. And SOTA results, where AZR matches or beats models trained with human data on coding and math benchmarks. Looking ahead, there's a lot of potential here. Future research could apply this approach to other domains like science or engineering, or scale it to even larger models. You might see AI systems that can teach itself entirely new skills, pushing the boundaries of what's possible. In conclusion, Absolute Zero is more than just a clever name, it's a vision for the future of AI, where models can learn and grow on their own. Thank you for joining me on this journey, and I hope you all are as excited as I am for this paper. Thank you.